To tackle the challenges offered by shift and screw, our team has divided the challenge into its two essential components. One is the orienting aspect, for which we have opted to use a vibratory bowl feeder, and the second is the aspect of picking up the screw using the drill and dispensing it to the place where the screw has to be drilled. The design of the vibratory bowl feeder is proposed to be almost exactly to industry standards. The screws are fed to the dispenser via the vibratory hopper, where they slowly make their way to the bottom of the main vibratory bowl. The hopper regulates the number of screws being dropped into the bowl using an Adafruit brake beam IR sensor. If the sensor detects a screw in the dropping position on the bowl, the door through which the screws are released into the hopper is closed. The door reopens once IR sensor detects an empty space, once the screws in the bowl move onwards and for the incoming screws. This regulates the number of screws being dropped into the bowl, so the system can be managed at industry level standards. Once in the vibratory bowl, the screws are moved towards the sides due to vibrations of the bowl. As the bowl rotates, the screws will go up the spiral because of the friction of the screws between the spiral and the bowl, which will allow the screws to start ascending the inclined plane. The rotation of the bowl will be generated using a 12-volt hobbyist brushless DC motor, and the vibration in both the hopper and the bowl will be generated using 12-volt vibration motors, which spin an unbalanced mass at 10,000 RPM to create the vibration. After reaching the highest level on the spiral, the screws move towards a system of rails wide enough to allow the tail of the screw to pass through, but not enough to allow the head of the screw to pass through. This will orient the screws head top. An Adafruit brake beam IR sensor will be placed near the end to count the screws as they fall into the desired orientation. We will use an HC05 Bluetooth module to communicate between the TI launchpad and wirelessly enable BeagleBone to make sure that the arm knows when the screw is ready to be picked up. This is to stop the feeder when there are too many screws waiting to be dispensed. Based on similar designs we have researched, the entire bowl feeder mechanism is expected to be powered by a 12-volt power supply for the motors and a 5-volt power supply for the TI launchpad, IR sensor, and Bluetooth module. Now, moving on to the EM drill attachment section. A 3D printed cylindrical plastic piece will be fitted around the drill bit clamping mechanism. We will then wrap copper wire around this piece to create a solenoid. The solenoid will create a magnetic field strong enough for the screws to stay firmly attached to the drill bit while the arm is in motion. This will prevent any screws from dropping during rapid movement of the arm. The solenoid will be wired to a 10,000 mAh battery capable of outputting 2 amperes of current, along with a switch actuated by a BeagleBone Black wireless microcontroller. The BeagleBone will communicate via Bluetooth with the TI launchpad controlling the bowl feeder in order to sync the arm's motion up with the availability of oriented screws. When the IR sensor on the bowl feeder is triggered, the UR5 robotic arm will navigate to the shaft of the bowl feeder and pick up the correctly oriented screw. The BeagleBone will communicate with the UR5 over a wired Ethernet connection using UR script. The screws will then be dispensed in the designated location.